Okay, all right. So a very good evening to all. Uh, so I am here to take this live tutorial session number 12, and this is the last tutorial session for this NPTEL course, Operation and Planning of Power Distribution Systems. So the last big chapter name is Distribution System Automation and Smart Grid. So in this tutorial session, we are basically going to see most of the problems regarding wind energy conversion system, and then we will see some also problems based on the distribution system automation and smart grid. Basically, we will see problems regarding comparison between the nowadays smart grid and with our conventional distribution system. And we will also see about some problems based on the SCADA, supervisory control and data acquisition system. So let us, as usual, first we will uh, revise the concepts regarding the problems we are going to solve today, and then we will start to solve problems, and in parallel you also try to solve problem, and you can type your answer in chat box. So let us begin with this wind energy conversion system. So how you will estimate the wind energy at a site? So the fundamental regarding that, first we need to know what is the amount of mass flow through the wind turbine. So the mass flow through a wind turbine can be depicted like these things: m dot equal to rho a u naught, where m dot is dm upon dt. So this is the mass flow that is flowing through the wind turbine. Now how you can how you can write the power available in wind p naught through an area a at a speed of wind turbine u naught. So this comes out from the expression p naught equal to half m dot u naught square. So this is the expression for the power available in wind. This is the power available in wind. So if you write the expression of m dot from this first one, mass flow rho a u naught, in this expression, then you will get half rho a mu u naught q. So this is very fundamental and basic equation that we need to know, and very important to solve the problem. Half rho a u naught q, where rho is the air density and a is the area of turbine blade, and u is the free speed wind, free wind speed. U naught is the free wind speed. Now you know this power available in wind. Now we know that we cannot utilize all the available power in the wind to convert into electrical energy. So what we can how we can find the electrical energy? So first we need to find the power extracted by wind turbine. So this P naught is the amount of power available in the wind. Now we will find the power extracted by the wind turbine. So to find the power extracted wind turbine, one coefficient comes that is known as power coefficient. So the amount of power that can be utilized by wind turbine is given by the power coefficient Cp, and its value varies with the rotor design and tip speed ratio TSR, that we also denoted by lambda. Therefore, the power extracted by wind turbine equal to power coefficient multiplication with power available in the wind. So Pt equal to Cp cross P naught. And if you want to know about this maximum value of this power coefficient, then it comes out as 0.59, and this comes from the Watt's law. So the maximum value of power coefficient can be 0.59, and its value is 0.59, and this is this comes from the Watt's law. So we know about how much the power available in the wind, that is half rho a u naught q, and how much power is extracted by wind turbine. And the next step is that how much power is converted into electrical energy from the wind energy. So the electrical power output will be efficiency into power extracted by wind turbine. So what is the efficiency here? So efficiency combines this your so efficiency combines here this rotor blade efficiency or your generator efficiency. So the efficiency of your wind energy conversion system multiplied with this power state by wind turbine will give you the electrical power output. So if you see here, the important thing is that you should know about power available wind, that is half rho a unit Q, and then after that, if you get the power stated by wind turbine, that is multiplied with power coefficient Cp into P naught. So you will get the power state of wind turbine. Now to get the electrical power output, you have to multiply it with the efficiency. And efficiency here is the gear generator efficiency. Some in the problem they have given this efficiency of gearbox and generator separately. So you have to multiply both efficiency to get the combined gear generator efficiency. So this is the all expression about the electrical power output from the wind energy conversion system. Now let us see some other terms that is very important. Another term is the TSR, and that we denote by lambda, and it is the relative speed of the rotor tip with respect to wind speed. So it is the ratio of rotor tip speed to the wind speed. And rotor tip speed is the tangential speed of rotor. Therefore, you can write rotor tip speed equal to R omega, and wind speed is written as U naught. So we know that omega equal to 2 pi n, where n is the revolution per second. And if you convert n revolution per second to RPM, then you have to divide by 60. Therefore, it comes out as 2 pi n upon 60. So the expression will be R equal to lambda equal to R into 2 pi n upon 60 into U naught. So here R is the rotor radius, omega is the rotor speed in radian per second, n is the rotor speed in revolution per second, and capital N is the rotor speed in RPM. So you should know about this expression. Tip speed ratio, that is R omega upon U naught. Other you can derive, just you know how to convert in other forms. Now another expression comes out here as how you can estimate the wind speed at height h. If you know wind speed at certain heights, then how you can estimate the at a different height by knowing the wind speed at certain height. So this comes this comes from this expression E equal to U naught into h upon h naught the power a, where a is the roughness of friction coefficient and U naught we know that is the difference wind speed at reference height h naught. So don't confuse with this free wind speed. It is the speed where given at the height h naught. And if you see according to WMO, World Meteorological Organization, we have this standard wind speed U naught is generally taken as the 10 meter from the ground. So this is the standard one that we taken from the that is with this reference to World Meteorological Organization. So these are all expression about the wind energy conversion system. Now let us see its power curve with respect to wind speed. So power curve shows the approximate power output as a function of wind speed. You can see this y-axis denotes power input, while x-axis denotes its wind speed. So this power curve shows this power available in the wind. Here if you see this minimum wind speed required to start the blades turning and producing a useful output is defined as the cutting speed. So the first one is the cutting speed, that is minimum wind speed required to start the blades. turning and producing useful output that we call it cutting speed. So this one is cutting. Before that, we cannot produce power from the wind turbine. Now another term is the rated speed. That is the maximum power output that the wind turbine will produce is called as the rated power, and it comes at the rated speed. So this is the rated speed, and then the last one is that shutdown speed. That after that we need to shut down our wind turbine. Otherwise, it will have severe problem in our wind turbines, and it may rupture or it may break down if you go more than that speed. That is called shutdown speed. So this rated speed is the minimum. You can also say that it is the minimum speed needed for the wind turbine to produce the rated power, because the maximum power is produced between the rated speed and the shutdown speed. So you can see that this is the minimum speed at which the rated power is getting, and shutdown speed is the maximum speed at which we are getting the rated power. And for the shutdown speed, there are other terms are also like furling speed or cutoff speed. So there are two other names for shutdown speed, that is called as furling speed or cutoff speed. And this is that uh, as, uh, beyond this shutdown speed, in order to prevent damage to the system from high winds, the blades are either folded back or turned to a high pitch position. So in order to prevent your turbine blades, you have to either fold it back or turn to a high pitch position so that you can save your turbine blades. So till here, this expression and this power curve is very important to solve the basic problems regarding wind energy conversion system. So I have I have shown all the important points about wind energy conversion systems, and all these expressions are very important. If you have, if you want to, means these are basic equations for wind energy conversion systems. So you need to know and you need to remember these expression also. And these are very simple expression. And power curve is also very important. Here three terminology are very important: cutting speed, rated speed, and shutdown speed. Cutting speed is the minimum speed. After that, turbine blade starts rotates and provide electrical power. And rated speed is the minimum speed at which it is providing the rated power. And shutdown speed, it is the maximum speed at which it is providing the rated power. So the maximum power you are getting between the rated speed and shutdown speed. So you can also tell here rated power or maximum power is obtained between the rated speed and the shutdown speed. And if you see this curve, that curve between this cutting speed and rated speed, this power is directly proportional to U naught Q. And how this proportionality come? This proportionality comes, we know that power available in the bin, we write it as half rho A U naught Q. So this is the expression for which it is showing this type of curve. That's why this power is coming as proportional to Q of U naught. Now we have some problems based on this constant speed bin turbines and variable speed bin turbines. You can refer to the SIRS lecture also. Lecture number, I think, lecture number 31, lecture number 32, 31. In 32, he has shown about the expression of this all expression regarding power available in the bin and power extracted from the bin turbine, and what is the electrical power output from the bin turbine. And in lecture number 31, you can have theoretical discussion regarding wind energy conversion systems. So depending upon the controllability, these wind turbine operating systems are categorized as two types: constant speed wind turbines and variable speed wind turbines. Constant speed wind turbines are having the following features. This constant speed stalled regulatory turbines have no options for any control input. These constant speed wind turbines have no options for any control input. It cannot vary its speed. Its turbine blades are designed with a fixed pitch. You cannot change its pitch for the turbine blades to operate near the originally tip speed ratio for a given wind speed. When wind speed increases, it causes a reduced rotor efficiency, and that is the limitation of power output. The same result can be achieved by operating the wind turbine at two distinct constant operating speeds by either changing the number of poles of the induction generator or changing the gear ratio. So what are the advantages and disadvantages of constant speed wind turbines? So this is simple, robust construction and electrically efficient design. They are highly reliable since they have fewer parts. They don't have current harmonics. Since there is no frequency convergence, they have a lower capital cost in comparison to variable speed wind turbines. On the other hand, they are aerodynamically less efficient and they are prone to mechanical states and are noisier. Now come to variable speed wind turbines. It has two methods for controlling the turbine operation in terms of speed changes and blade pitch changes. The control strategy that are usually used are power optimization strategy and power limitation strategy. The power optimization strategy is used when the wind speed is below the rated value. It optimizes the energy capture by keeping the speed constant based on the optimum TSR. However, if speed is changed because of load variation, the generator may be overloaded for wind speed above nominal value. To prevent this, methods like generator torque control are employed to control the speed. And the power limitation strategy is used for wind speed above the rated value by changing the blade pitch to reduce the aerodynamic efficiency. And coming to this advantage and disadvantage of variable speed wind turbines. The advantages are these are subjected to less mechanical stress and they have high energy capture capacity. They are aerodynamically efficient. We have seen that the constant speed wind turbines are aerodynamically less efficient, and whereas these variable speed wind turbines are efficient aerodynamically and have low transient torque. They require no mechanical damping system since the electrical system can effectively provide the damping. They don't suffer from synchronization problems or voltage sags because they have a steep electrical controls. The disadvantage of the variable speed wind turbine system include this following. They are more expensive, they are require more complex control strategy, and they are electrically less efficient. So this is all about our summary for today's tutorial session. You can go through your own regarding this distribution system automation and a smart grid, and you can refer from the lecture 35 where you will go regarding a SCADA system and demand distribution automation. So they have sir has shown in many slides regarding this automation and distribution automation and a SCADA system. So these are very means the question based on this automations, distribution system automation and smart grid are very easier. So I have not covered that part. So you can refer from the lecture 35. So let us solve the problems. So first problem is shown over here, and this okay, DV and Guddu, are you able to see the screen? Actually, there was problem in the network on my side. Okay, okay, Guddu. Till here, any doubt you can ask. Otherwise, we can solve the problem. If you don't have any doubt, you can start solving this problem number one. So this first problem is of multiple select question. So we have just seen about the constant speed wind turbine and variable speed wind turbines. So it is telling about which of the following statements are correct regarding the wind turbine operating systems. The first option is power limitation strategy is in variable wind speed turbine due to thermal limitation of generator. Second option is power limitation strategy used in variable speed wind turbines due to mechanical constraints of the wind turbine. The speed of constant speed, C option is that the speed of constant speed wind turbines can be varied by changing the number of poles of induction generator or by changing the pitch of blades with only limited positions. And D option is that variable speed wind turbines are electrically less efficient while aerodynamically more efficient. So you can give your answer in chat box. I am waiting for 1 or 2 minutes. Okay, Guddu is saying B and C, while Dev is saying D and B. Dev, your answer is correct. B and C are correct. B and D, sorry, B and D are correct. So if you see the first option, power limitation strategy in variable speed turbines due to thermal limitation of generator. So there nothing about thermal limitation generator, so it is incorrect. B option is power limitation strategy using variable speed wind turbines due to mechanical constraint of the wind turbine. This one is correct. C option is the speed of constant speed can be verified by changing the number of poles of induction generator or by changing the pitch of blades with only limited position. So no, we cannot change the pitch of blades in the constant speed wind turbines. So it is also incorrect. While D option is variable speed wind turbines are electrically less efficient, while as aerodynamically more efficient. Yes, it is correct. It is more efficient aerodynamically, while it is less efficient electrically. So B and D are correct options for this first number problem. Now let us see the second number problem. A wind turbine with blade radius of 5 meter has cut in a speed, rated a speed and cut out a speed as 4 meter second, 25 meter per second and 45 meter per second respectively. So in this problem, they have given about cut in a speed, rated a speed and cut out a speed. The efficiency of gearbox is 70% and efficiency of turbine generator is 90%. The air density is 1.24 kg per meter cube and the turbine power coefficient is 0.3. The output powers of the wind energy conversion system for cutting a speed, rated speed and cut out speed are respectively. This is very important problem regarding wind energy system. So here you will know the concept of power curve with respect to various wind speed. So I am first writing what are the things they have given in the problem. So they have provided you the radius. So the radius of blade is 5 meter. Cutting speed cutting speed they have given you as 4 meter per second. While rated speed they have given you as 25 meter per second. While cut out speed they have provided you as 45 meter per second. Efficiency of gearbox they have given you as 70% or 0.7. Efficiency of generator efficiency generator is 0.9 or 90%. And air density is given as 1.24 kg per meter cube. And turbine power coefficient we denote by Cp, that is given as 0.3. The output powers for cut-in speed, rated speed, and cut-out speed. You have to find. So let us find first the at cut-in speed. So let us find the electrical power output at the cut-in speed. So the first part is that we need to find electrical power output at cut-in speed. So we know that we start from the first expression. We know that power available in the bin is half rho A Q naught Q, and then PT comes power extracted from the wind turbine. This power coefficient term comes that we don't know as PT equal to Cp into P naught. So Cp equal to PT equal to Cp into half rho A Q naught Q. Then we have the term electrical power output, that is you combine gear generator efficiency into power extracted from the wind turbine. We are going to use this expression. So let us expand it. So electrical power output, first you write the efficiency of gearbox, and then efficiency of generator, and PT we know PT Cp into half rho A Q naught Q. So this is the expression for power output from the wind turbine. So you substitute all these values. So they are telling about the cut-in speed. So cut-in speed is given as 4 meter per second. So U naught, this is U naught. So U naught is given as 4 meter per second. So gearbox is 0.7, generator efficiency is 0.9, and then Cp is given as 0.3, half rho is given as 1.24, area is pi r square, so 5 square, and U is given as 4 meter per second. So if you do it, then it will come as electrical power output as 589.011 watt. So this is the electrical power output at the cutting speed. Now let us find the electrical power output at the rated speed. Electrical power output at the rated speed. So rated speed is given how much? Rated speed is given as 25 meter per second. So just we will put values. So at the place of U naught, we will put 25. So electrical power output is gearbox efficiency, then generator box efficiency, then 0.3 is CP power coefficient, and then half rho is 1.24 kg per meter cube. Area is pi r square. Radius is 5 meter per second, and U is 25 meter per second. So if you do this, then you will get electrical power output at the rated speed as 143801.495 watt. So this is the electrical power output at the rated speed. So here these are the options. So what do you think? What should be the correct answer? I am giving you 2 minute time. Give me the answer. What should be the correct answer? And we got this electrical power output at cutting speed as 589.011 watt, while electrical power output at data speed we got as 1,43,801.495 watt. Now we have to find electrical power output at cutout speed, and you have to find the answer from these options. I'm coming in one minute. Guddu is saying C. Div. Maybe what is your answer? We got the electrical power output at continuous speed this much, and we got the electrical power output at the rated speed this much. Now you need to find the electrical power output cut out a speed and kill the answer. Yes. Cut out speed the maximum speed. We cannot operate above the cutout speed. So at cutout speed also, this speed is same to the rated speed. So if you see this power curve, then you can understand better. It's better to copy. Put it here. So here you can see that this electrical power output at shutdown speed is same to electrical power output at the rated speed. So you can write 1 point. Electrical power output at cutout speed or shutdown speed or furling speed or cutoff speed, same as electrical power output at rated speed. We have found the electrical power output at rated speed. Just take it as third. Electrical power output at rated speed is 1,43,801. So 143,801.495 watt. So if you match from the options, then C option is matching with this option. C option is correct. Now let us come to the next problem. So here a 240 volt 5.76 kilowatt single phase load is supplied by a solar plant having identical solar cells of rated power 30 watt and rated voltage 20 volt. Determine the number of solar panels required to be operated and their arrangement for supplying the load if each solar panel is able to generate only 80% of its rated power. And the options are shown over here. So if you see first this type problem, you first find the number of series connection and number of series connection of solar panel you can find from the voltage. So if anyone got the series connection, just let me know. Otherwise, so first find the series connection. What is the series connected? What is the number of series connection of solar panels? Yes. Series connection is 12. Yes. Dev, your answer is correct. So how we can find the series connection? So it is given the load characteristics. So load is of 240 watt, 240 volt, and the rated voltage of identical cell is given as 20 volt. So if you connect solar panels in series, so they have provided the uh, solar panel is operating at rated voltage of 20 volt. So let us take as 1, 2, and n number of series connections. So if there are n connections, and this is connected to the load, and load is of single phase load. Anyhow, this is DC supply. Supply noise, no meaning of single phase. And the load is of given as 240 volt. So this is given as 240 volt. So you multiply 20 into n series connection, that is 240. Therefore, you will get n equal to 12 number of series connections. Now we have found the series connections. Now we have to find the parallel connection of this solar array. So we have one solar module that are connected series connection that is providing power at 240 volt. Now we have to find the number of parallel connection. So parallel connection we will find from the power rating. So it is also given that this our solar PV is able to generate only 80% of its rated power. So each solar panel is of 20 volt and they are of 20 volt and they are able to have power generation capacity is 30 into 0.8. So 24 watt. I can write it here separately. Power generated by each solar panel equal to 30 into 0.8, that is 24 watt. So it is given as 24 watt. And now we know that 24 watt solar panel is connect, 12 number of 24 watt solar panel connected in series. So one solar array that is connected in series is how much providing the power. So if you see this one is similar like the another case, means another one is connected like this one only. So you can write this is the first number of series connection, and this tell it as m number of parallel connection. Sorry, first number of parallel connection, then it is m number of parallel connection. So one from the one module that are having n number of solar panels, so they are providing power how much? So it is providing power 24 watt into how much parallel, how much number of solar panels? 12 numbers. 24 watt into 12. So it is coming as 288 watt. And we know that this power requirement by the load is 5760 watt. That is the load specification. So we know that from each module we are getting 288 watt. Therefore 288 watt from each module. We have m number of module, and that comes equal to 5760 watt. So m number of parallel path you can find 5760 upon 288. So it will come as 20. So 20 number of parallel connection. How many of you get the same answer? I don't know why they have written this single phase load. Yes, Div, your answer is correct. First A option is correct. A series path of 12 panels and 20 such parallel paths. So A option is correct. Now let us come to the next problem. Determine the power generated by a solar plant if the connection of one of the solar panel breaks open due to fault in the arrangement. In question 3. So we have found the number of series and parallel. So I am just giving you the data and you find the answer. Number of solar panels we have found this in previous problem. Number of solar panels connected in series, it comes out as 12, and that number of parallel path means the number of parallel connection of module is 20. Load is of load characteristics is of 240 volt and 576 kilowatt, 5.76 kilowatt. While solar cells You can either write solar cells or solar panels. It's better to write solar cells. Solar cells of ratings of 20 volt and 30 watt and efficiency E of is 80%. So it is solved. To try this problem, I am coming in. I got one option B. Yes, Dev, your answer is correct. Very good. So if you are solving here, I am 100% sure that you will able to solve in the exam also and you will get good mark, good grade. So here, what is the concept that you are one solar panel breaks means one solar cell breaks. It means that whole parallel path will be eliminated from the power generation. So this is the concept. You can write since one panel develops develops open circuit because solar panel breaks open due to fault. Develops open circuit which results in the elimination of whole parallel path. Whole parallel path. Therefore, power generated by the plant power generated by the solar plant equal to total generation is 5760 watt minus from each panel how much we getting 24 watt into 12 series panels. So it is 5760 watt minus 288 watt. So 5472 watt. It is equivalent to 5.472 kilowatt. So B option is correct. Very good, Dev. Your answer is correct. So now let us move to the next number problem. Question 5. So in the problem here it is saying that voltage and current of a solar cell with surface area of 2 centimeter square are 0.408 volt and 801 milliampere respectively at 45 degrees centigrade. Determine the rated voltage and current of solar cell at 25 degrees centigrade. So here I want to give you two expressions. I am give you two hint to solve this problem. The voltage of a solar cell you can find if they have given the voltage at a specified voltage. So they have given at 25 degrees centigrade. So this expression is E naught equal to ER minus 0.0021 T minus 25 volt. And the current generated by solar cell is I naught equal to IR plus 0.225 A into T minus 25 milliampere. So these expressions are very important. So if you see in the question 5, they have given E naught and T. Means T is they want to find you at 45 degrees Celsius. And E naught is given as 0.40 0.408 volt. Similarly, I naught is given as 801 milliampere, and this this is not yes. So this two expression you need to know and keep in mind that in the current generated by solar cell, here area is in centimeter square. I naught equal to IR plus 0.0025 A into T minus 25 milliampere. So here I naught is the current in milliampere at temperature T degrees Celsius. IR is the rated current in milliamperes of the cell at temperature 25 degrees Celsius. And A is the surface area of the solar cell in centimeter square. So we need to know this expression, then we can solve the problem. So let me copy this. So this expression I am providing you now. You solve the problem and let me know the answer. So if you see from the problem, let us write what are things they have given. So given are surface area. Surface area means area they have provided. So area they have provided as 2 centimeter square. And then voltage and current of solar cell at 45 degrees Celsius they have also provided. Sorry, at 25 degree. At 45, and you need to find the at 25 degree. Okay. So this the ER is given as 0.408 volt and IR is given as 801 milliamperes. Sorry, I earlier said that it is given 25 degree. Sorry, they have provided the question as 45 degree, and you have to find the voltage and current at 25 degrees Celsius. And we need to find E naught and I naught. All the things we have given, and temperature they have provided at 45 degrees Celsius. So let us first find E naught. So E naught is ER minus 0.00 T as 25. ER is 0.408 minus 0.0021. T is 45. Point 408. One minute, I am confused with plus minus sign. Yes, Dev, your answer is correct. Very good. Point 0.45 volt. Sorry, it is plus. Plus. It was minus. I have done a mistake. Sorry for this mistake. Now it is correct. Now second number is we have to find I naught. I naught is IR minus 0.0025 A into T minus so I naught is IR given as 801 milliampere minus 0.0025 into 2. Temperature is 45 minus 25. I naught is 800 milliampere. The voltage is increasing while current is decreasing at lower voltage. So therefore the correct answer from this options are B is the correct answer. D is the correct answer. Devi, you had applied same expression or some another expression to solve this problem.
Sir, I used the first expression. When the sign is changing, the answer I'm getting is changed. That is 0.366.
What?
If it is
Which,
E0 equal to ER minus 0.0021, then only the answer is 0.45.
how?
We are finding out ER, right? E0 is given at T degrees Celsius, right?
Yeah, then E naught. No. We have to find the E naught at 25 degree. In the problem, you see, determine the rated voltage and current of solar means you are referring this equation or some other equation.
No, this equation only, sir.
Then here it is written we have to find the at voltage and current at 25 degrees centigrade. E
Yeah,
naught
so E0 is given is the
not
given
given.
value, right, sir?
No, not given. ER given.
Okay.
So that was mistake in the expression. ER and I are given and they are the data provided at 45 degree means ER, IR and temperature is given and we need to find E naught and I naught that is at 25 degree. There are some other expression also.
Sir, previous slide. Can you please show the previous slide?
This one.
No. That 17th slide. Yes. Here it is given like E0 is the voltage in old set temperature T and ER is the rated voltage at cell temperature 25°. So that was what,
Confusing.
yeah.
That's why I'm wondering why I have done a mistake. Yeah, correct. Oh, God. Okay, I am also today I am a little bit out of mind. I have written here also. E naught and T is given. We have to find ER. So earlier it was correct. Yes. That's why I'm wondering. Miss equations I have referred. That is correct. To find ER not E naught. Okay. Let me correct. So this is E naught, I naught, and this is ER. This is IR. Yeah, I'm a little bit out of mind today. Sorry, I'm also not feeling from the morning bell. Then no problem. So now I think it is okay. So E naught is the voltage at temperature T and ER and IR is the voltage at the 25 degrees Celsius, right? And we have to find ER and IR and E naught and I naught it is given. So E naught, ER we have to find by now IR. Now I think it's perfect. So D option is the correct answer. So anyway, you just go through these equations and you will get this answer. There are some other ways also. You can know about the how these equations came. So you can get from that basic equation also. Now let us come to the next problem. So in this problem 6, a wind energy conversion system uses a 3-phase 6-pole induction generator. The line frequency is 50 Hz and the wind speed is 10 meter per second. The turbine blades have radius 25 meter and peak efficiency when TSR is 9. If the generator efficiency maximum at negative slip of 3%, determine the transmission gear ratio corresponding to peak speed efficiency. So let us write what are things given. Number of poles, they have provided 6. Frequency, they have provided 50 hertz. And wind speed, that is u naught, given as 10 meter per second. And turbine blade radius is 25 meter. Peak efficiency and peak efficiency when TSR is 9. Lambda is given as 9. The generator efficiency is maximum at negative slip of 3%. Determine the slip is given as 0.03. Transmission gear ratio. So I will just provide you here one expression also. So transmission gear ratio is this speed of generator rotor in generator upon this turbine blades, the speed of turbine blades in turbine. So this expression we need to know, that is the gear ratio, the speed of generator rotor and the speed of turbine blades. The speed of rotor generator to the speed of turbine blade. So we have to find both these expression. The speed of generator we will first find. Let me change the color. So the speed of generator is given by the speed of generator is given by in generator one plus S 120 F upon P, where F is frequency and P the number of poles. So S is 0.03, 120, frequency is 50 hertz, and number of poles is 6. Therefore, it will come out as 1030 RPM. So this is the speed of generator we got. Now how will get the speed of turbine blades? For the speed of turbine blades, we can use this TSR. So TSR or lambda T plus speed ratio or lambda, we know that R omega upon U naught. So we know lambda R U naught, then we will get the omega. That is the angular speed of turbine blade. So lambda is given as 9, R is given as 25, omega we got, U naught is given as 10 meter per second. So omega we got as 3.6 radian per second. So first convert radian into revolution. So we know that in one revolution 2 pi radian. So we need to divide by 2 pi to get it in, a revolution per second. 3.6 upon 2 pi, that we call as revolution per second. Now we have to find the revolution per minute. So multiply by 60. So we'll got revolution per minute. Right? This expression is okay. So if you do this, 3.6 into 60 upon 2 upon pi, then you will get 34.38 RPM. So now you put, so it's better to write separately. If you got omega, then you will got revolution per second, that is turbine blade n turbine blade, that is 3.6 upon 2 pi RPS. Now you will get n turbine as 3.6 into 60 upon 2 pi RPM. That is 34.38 RPM. Now you know n generator and n turbine blade, then you substitute in the gear ratio, you will get the gear ratio. So, n generator speed is 1030, while turbine blade is 34.38. So if you do this, then you will get 29.96 is the transmission gear ratio. Any doubt in this problem? Yeah. Any doubt in this problem? Deep and Guddu.
No, sir. No, sir.
And one problem is similar to based on this this problem in the current assignment. Have you seen that? Have you gone through that?
No, sir. I have to note it.
So I would suggest that if you get the answer, then it is okay. Otherwise, you can ask in the discussion forum. I think it might be some problem in that question. I'm not confirmed, but those who I'm not setting up the assignment question. They do sometimes do mistake in providing the option. So question number 3 in assignment 12, it is similar type. They have asked about they have given the transmission gear ratio, but in that problem they are asking the wind speed, and they have given the same option. I think there might be mistake. So you can ask in the discussion forum so that they can correct it, or they will might remove the problem.
Okay, sir.
Yeah. And brief summary about this question 6 is given here. It's like what is the transmission gear ratio? that is the ratio of speed of generator to the speed of turbine blades. The speed of generator rotor is given by this expression, and from the T per speed ratio, you can find the speed of turbine blade. So for finding the speed of generator rotor, you will use this expression 1 plus s into 120f upon p. And to find the speed of turbine blades, you use the T per speed ratio expression. Now let us come to the theoretical problems. Question number 7. Which of the following statements are correct in context of distribution network? And this problem is of multiple select question. More than one options are correct. So first option is that passive networks are only suitable for residential areas, whereas active networks are designed for industrial applications. B options are B option is active networks are exclusively AC based, whereas passive networks may use both AC and DC technologies. C option is active networks incorporate power tonics, advanced sensor and measuring infrastructure and intelligent control, while passive networks lack such advanced features. D option is passive distribution networks are more resilient to cybersecurity threats than the active distribution network. Can give your answer, then we will start the discussion. Kudu is saying BA, while Dev is saying CD. Dev, your answer is correct. C and D are correct answer. So let us see the first option. Passive networks are only suitable for residential areas where active networks are designed for industrial application. No. Usually, our old conventional distribution networks that they are passive networks, while due to integration of DG, EV charging station, and all these things, this leads to transformation of our network into active type. That's why you cannot bifurcate why this application wise. They are suitable for both application, but due to integration of renewables and EV charging station, our uh, conventional distribution networks become changes into active type. B option is active networks are exclusively AC based, whereas passive networks may use both AC and DC technology. It is also incorrect. Active networks are not AC based, and it is based on the means like earlier in passive networks. What happens that power there is unidirectional power flow, while in active networks there is bidirectional power flow. You can exchange the power to the grid. You can take the power from the grid also, and you can provide the power to the grid also. Active networks incorporate power tonics, advanced sensors, and measuring infrastructure and intelligent control, while passive network lack such advanced features. Yes, it is correct. In active networks, we have power tonics devices to integrate the renewables, advanced sensors to sense the voltage and current so that we can synchronize our inverters to the grid, measuring infrastructure. Yes, we are sensing various electrical quantities, and so that have we can have supervisory control over power flow And we have intelligent control also, means which DG should be incorporated, which when what is the status of each DG and how much they are providing power. It is all are controlled in very intelligent way. While passive network lack such advanced feature, yes. Passive network means our conventional distribution system. C option is correct. Passive distribution networks are more resilient to cyber security threats than active distribution network. Yes, it is also correct. In passive networks, we don't have any communication features, so there is no threat of uh, cyber. There is no cyber threat. But in our active distribution, there are so many communication and there are so many sharing of data happening. So there is always threat of cyber. They are not active distribution networks. They are not resilient. That are not more resilient towards cyber security, while passive distribution networks are more resilient to cyber security. Now coming to the next problem. Which of the following statements is correct about the reliability of microgrids as compared to that of conventional distribution networks? And the options are: microgrids have lower reliability due to their reliance on intermittent renewable energy sources. Microgrids typically have higher reliability as they can operate independently during grid disturbances. Both microgrids and conventional networks exhibit similar level of reliability. And D option is conventional networks are more reliable due to their centralized control systems. Yes, anyone? I got some responses. If is saying D, no, D is not correct. D is also not correct. Did you get this problem? So I am just explaining each options so that you can tell me. The first option is that microgrids have lower reliability due to their reliance on intermittent renewable energy sources. No, microgrids have higher reliability due to the presence of power generation at the locality, because we can either we don't have, if there is power disturbances from the grid, we can go in isolation mode. Microgrid can go in isolation mode, isolated mode, and they can provide their power on their own. So they have more reliability due to the integration of renewable energy sources. So it is incorrect. B option is microgrids typically have higher reliability as they can operate independently during grid disturbances. Yes, it is correct. So B option is only coming correct. C option is both microgrids and conventional networks exhibit similar level of reliability. No, conventional networks have lesser reliability because if the grid disturbances, your power will be cut and there is no power supply from the grid and there is no other options for you also. It's how you will take the power from any other end if you don't have any reliance on the renewable resources or you have a separate microgrid. Conventional networks are more reliable due to a centralized control systems. No, it is also incorrect. If you have centralized control system, means like you are sharing the data all to the centralized system, and centralized systems have lesser reliability than distributed control system, because in centralized systems you are, if there is, first of all, if there is have communication failure, or if you have uh, if there is mismanagement in control, means providing the set points, then there higher chance that your network goes into unstable region and you cannot provide the power. You have to interrupt the power supply when this happens. So conventional meters are less reliable and centralized control systems are not more reliable than distributed control system or decentralized control system. I hope it is clear. Okay, let us move to the next problem. Here in this problem regarding real-time monitoring and control, which of the following statements distinguish the capabilities of smart grids from conventional grids? And options are this given below, and options are quite little bit lengthy. And this problem is of multiple select question. So let us go through one by one each option. First option that conventional grid use outdated monitoring systems with limited data collection, while smart grids deploy advanced sensor and communication technology for real-time monitoring. Yes, it is correct. You have to just use your presence of mind, means like what are things. If you have going through your daily newspaper, also you are able to answer this type of question. B option is smart grids utilize advanced real-time monitoring and control seamlessly enabled with only unidirectional communication link. No, it is incorrect. There is no unidirectional communication links. We have bidirectional communication link. While as communication conventional grids do not use monitoring and control system. It is incorrect. It is correct only, but here unidirectional communication link comes. So this becomes incorrect. Smart grids use advanced two-way communication for real-time monitoring control, while conventional grids primarily use one-way communication. Yes, it is correct. Smart grids, despite their emphasis on advanced technology, struggle with real-time monitoring as they primarily rely on outdated monitoring mechanism. They really don't struggle with real-time monitoring, and they don't have outdated monitoring mechanism. They have advanced monitoring mechanism. So it is also incorrect. So A and C options are correct. Now let us come to the last problem. So which of the following statements are correct about the difference between microgrid and a smart grid? So let us go the go the option first by first. The first option is that a smart grid is a small localized part of distribution network with advanced information and communication technology, while as a microgrid is a part of distribution network where DG units are connected. No, a smart grid is not a localized part of distribution network. So this statement itself incorrect, and this is correct. Macro is part of distribution network where DG units are connected. So second statement is correct, but first statement is incorrect. So therefore it is incorrect. A macro grid is a localized part of distribution system. Yes, it is correct. That can operate independently or in grid connected mode, while as in a smart grid is an extensive modernization of the entire electrical grid with advanced communication, control, and monitoring technology. Yes, it is correct. The option is macro grid can be considered as a control entity only in grid connected mode. No, it is control entity in both islanded and grid connected mode. So it's not control entity only in grid connected mode. It is control entity in both islanded and grid connected mode. While a smart grids is always considered a controllable entity. Second statement is correct, but this one is incorrect. Macrogrids may have a mix of renewables and non-renewable sources, while a smart grids always have only renewable source of energy. It is incorrect. It has both conventional and both this coal-based plant also, and we have renewable-based resources also. So this is incorrect. So B option is correct. Still here any doubt you want to ask? Yes. Yes, for question 9, A and C are correct. So in the problem, I want to tell you something. In this problem, so here they are asking about the voltage and current at 25 degrees Celsius. So here I will tell you that current in solar cell is positive temperature coefficient. So in current in solar cell is having positive temperature coefficient, and voltage is negative temperature coefficient. What do you mean by negative temperature coefficient? Negative temperature coefficient means T decreases as temperature increases. Now we verify these statements. We have given E naught equal to 0.408 volt. That is given as point, and that is given as 45 degrees Celsius. Now they are asking 25. So it is increasing. So it is verified from this statement. We have E naught 0.408 volt at 45 degrees Celsius. So at 25 degrees Celsius, it is having higher value. So ER, we are coming as 0.45 volt. That is at 25 degrees Celsius. So this statement is verified. So there are 2 points I want to say here. First is that voltage of solar cell is of negative temperature coefficient, while current of solar cell is of positive temperature coefficient. I is of positive temperature coefficient. And what do you mean by positive temperature coefficient? Current will increase as temperature will increase. So let us find I naught. I naught is given as 800 milliampere at 45 degrees Celsius, and we got IR higher as 800 milliampere at 25 degrees Celsius. So if you know this thing, like what is the nature of voltage and current for solar cell, then you can also, without solving, you can get the answer, get the answer for this problem. Like they are given at 45 degrees Celsius for voltage. Now you know that voltage 25 degrees Celsius, it must be higher. So this A and C options are cut down. Now we have two options, B and D are two. Now you have verified for voltage. Now you want to know for current. Current, you know that it is positive temperature coefficient. Means at 45 it is 800 1 milliampere. So it must be less at 25 degrees Celsius. So in B option it is higher. So it is incorrect. Now only you have one option. D is correct. So D option is only satisfying that voltage is of negative temperature coefficient while current is of positive temperature coefficient. Did you get my point? You can solve this problem without using any expression.
Yes, sir. Yes, sir.
Yeah. So I just clicked my mind because I had taken session in the design of photovoltaic system also, but in that course we have given the temperature coefficient, and from the temperature coefficient we can easily find the voltage and current of solar cell. Means there they are talking about short circuit current and open circuit voltage using the temperature coefficient. So in that course it is little bit quite different way, but this concept you can use anywhere. And in that course we don't have used this expression. We have used the coefficient type expression, like current coefficient, voltage coefficient, power coefficient. And now you have voltage and current of this type. Now you tell me, power is of negative temperature coefficient or positive temperature coefficient? You know that voltage is of negative temperature coefficient and current is of positive temperature coefficient. And what is the about power of solar cell, power output of solar cell? Div, it is of power is of negative temperature coefficient or positive temperature coefficient?
Negative, sir.
Yes, correct. Very good. It's simple. We know that power is V into I and negative into positive is negative. So if they ask about power also, you use this basic one. Means power is of negative temperature coefficient. If power is given at certain temperature, you just correlate. It should increase or decrease at if you divert from that temperature. So that is the trick. And this comes from this your IV curve. So a little bit quite interesting. You can see the IV curve. Different temperature. See, So if you see here, this voltage, see the current is of increasing temperature means increasing current. While here if you see increasing temperature reduces power out, and this voltage is also reducing, right? So at 0 degree, this voltage is maximum, and then at 25 degree, the voltage reduces while current is increasing. So this concept comes from this verifies from the IV curve of solar cell also. Here you see voltage. See the voltage is reducing on increasing temperature while current is increasing. So current on y-axis, voltage on x-axis. Voltage reducing on increasing temperature while current is increasing on increasing the temperature. So anyway, that is not our domain, but for extra knowledge, I have just shared this with you. So now I will just tell you means two problems from the current assignment are similar to the previous year assignment. You just go through all this problem. Like one problem of current assignment, question number 10. Optimal network configuration is part of the following smart grid initiative. So it is already from the previous year problem. So you also go through the previous year. So I will show you that problem has been asked in 2022. So this problem, optimal network is a part of following smart grid setting. So it is directly asked from the previous year. So you can get the answer from there. And about a smart grid also, this problem has been asked in previous year. So you go through the previous year theoretical problems also so that you can solve the current year assignment. Okay. Any other thing you want to ask or you want to discuss? Otherwise, we can close today's session. And one important thing is that tomorrow we have revision session at the same time, 7 to 9. And that is the last session for this course. I hope you all will get good marks and good grades in the exam. If you just able to solve the assignment, if you are solving assignment honestly, that is most important thing. If you have solved assignments and revise that, then you will certainly get sufficient marks. And if you want to have excel means like you want to have means topper category, then I would say that you just go through the class materials, you just revise through the video lectures, and you will get Elite Plus Gold certificate. But assignment is the first and most important thing. First try on the assignment, because I think most of the problems will be similar to that, because whatever exams I have given in PTL, in Olympic exams, they certainly ask similar type of the assignment problems. But that is not correct always. It's just it's my it's my advice.
My question, sir.
Yes,
Ganguly sir, recorded video is important for final exam, sir.
recorded video Means like if you want to means if you know the concept, then you can. If you don't know the concept, then you watch more and more. If you know the concept, then no use of watching video again and again. Right?
Uh, you have a 12 video solving that problem. Same as same questions are repeated in the final exam, sir.
No. Means that is means I am telling about that you know all the questions, means whatever we have discussed. I know you know how to solve. Watching the video is not important. If you know how to solve, it's your own way also. Means whatever way I am solving, it is not that the same approach you are following. You have different approach also. I am just showing it my way. I'm just discussing in more elaborate way and in better way so that each and every student can understand. But you can apply shortcut also for understanding. But important that you just revise all the problems. That is only important. Revise all the problems, and watching video is not thing that will be very difficult, because 2 hours video, who will watch? No one has that much time.
More time as spending, sir, in the recorded video lecture.
Recorded video, I would say that you should not mind video, but sir video you should once watch, because it will uh, enhance your mind also, means broaden your mind about what are things
Recorded
going.
video, is it important or not, sir?
Recorded video, if you don't know how to solve the problem, then it is important. Otherwise, it is not important. Because I'm not telling you very big concept. I'm telling you just what is how to solve the problem. If you know how to solve the problem, then it is not necessary. If you don't know, then just go through once.
So weekly videos are uh, attending. So it is enough, na, sir. Different types of question solving in the assignment. In
Yeah,
the
it is
TLA.
enough. It is enough. And you have I would say that you have a notebook where you have solved the problems, mostly problems, just to revise before exam. That is important. That I would
Yes, sir.
that suggest. Otherwise, what you will miss, and no one has time to watch so long videos. No one has time. That is first thing.
Thank you, sir.
Okay, then we will meet tomorrow, and the meeting link is same. And good night.
Good night, sir.
Okay, bye.
As a strategy, how to prepare tomorrow video, sir.
What?
Tomorrow lecture will be discussed on the overall how to prepare for the final exam.
Tomorrow. Oh, yes. Not yeah. Tomorrow we'll discuss. We will focus more towards
Next
exam.
topics are not started, no, sir. Tomorrow, next topic.
No. This is finished. Means our course is finished. Just we will revise all the parts tomorrow.
Okay, sir. Okay,
Yeah.
sir.
Okay. Bye.